Hey, this is video 1.2.7 where I'm showing you all the basics of how to write proper limit notation as we start to write more calculus language. So I'm going to share this whiteboard screen. So right here, I have a limit notation that I will work to connect back to function notation a little bit, but also give you all some intro on like how do I say this correctly. So right here, this reads the limit as x approaches -2 of f of x. I want to be clear in that limit notation is asking the same question as function notation, just slightly different, I'd say slightly differently worded. Every limit is still curious about what's the y value. Every limit's asking, hey, like as the function gets closer to this x value, what is the y value? So what you're seeing right here at its most basic level is still asking, what is the y value? It's still asking that. A limit and function notation are curious about the same thing. The way we would say this, go back to green, because I want that green. The way we'd actually say this in proper calculus language is the limit as x approaches -2. That arrow to the number is saying as it gets closer. It's not saying equals to, it's saying as we approach it. So as I get closer, if I were to follow it on the graph, I'll show you in a second, as I approach it, it's asking what's the y value. So the limit as x approaches -2 of the function f of x. Before I do the next one, I want to show off like what this is really getting at. So let me stop sharing this and share my Desmo screen. So this is the function f of x, and we just have this limit notation written down. We just have the limit as x approaches -3, I believe, of the function, it was -2. I should know that. It was -2, I'm glad I did that. Okay, so we were being asked, what is the limit as x approaches -2 of the function f of x? If we were dealing with function notation, we would ask, okay, like what is f of -2? To find that, we plug it in, we get this ordered pair when x is -2, looks like y is -6. Limit notation is asking a very similar question, but the difference is, it's like cautious, where it's like, okay, if I approach -2 from, we say the left side or from smaller values, basically if I'm just on the function, I'll show that more clearly. If I'm directly on the function, like I'm creeping up the function towards where x is -2, as I approach from smaller values than -2, and then as I approach from bigger values, we're still asking the same question. We want to know like what is the y value, what is the output value. So in this case, the limit and the function notation both produce the exact same outcome, because as we approach -2 on the function, it looks like the y value we approach is -6. I'll show off in the next one why that's an important distinction, but at the most basic level, limit notation and function notation are both asking the exact same question. So now let's get back to some wording. So if I see this, the way I'd write this would be the limit as x approaches infinity. And what you really could say, to be a little more accurate, would be as x approaches positive infinity. If you just say infinity, it's kind of assumed you mean positive infinity, but you can approach positive or negative infinity. Positive infinity just refers to, as on the x-axis, as x values get bigger and bigger on the positive side, eventually they go off to positive infinity. And then as x values are on the left side of the x-axis going more and more negative, they eventually approach negative infinity. So I get to the limit as x approaches positive infinity of, and I can just say of g of x. I can say of the function g of x or just of g of x. Pause real quick and see if you can do the purple one before I give you the answer. But I'm going to dive right in. I hope you paused. And then the way we'd write this one would be the limit as x approaches 4 of the function, or just of m of x. And all these questions are asking the same thing. As I get closer to 4, what's the y value on the function m of x? As I get closer to positive infinity, what's the y value? And I'm going to analyze this for m of x and g of x real quick, because I'll show you where function notation kind of fails us, but how limit notation is actually really cool and helpful. So here's m of x, just I wrote a random function for it. We're being asked, like, what is the y value as we approach 4? So the way we actually would analyze this with kind of limit calculation is we want to first identify where x equals 4, which it looks like, yeah, I should do this on the function first. So if I'm on the function, looks like right, so close. Right there is where x equals 4, right? The way we'd analyze that as a limit is we would kind of follow that function along from both sides, right? Okay, as I get closer and closer to that value from smaller values, as I get closer and closer to that value from bigger values, you know, what y value is being approached from both sides. And you saw in this case, if we approach 4, the y value is -2. That's why the limit as x approaches 4 of the function m of x is just -2. So again, very similar so far to function notation. It's a different way of analyzing, but end result is the same. So now I bring it up to say, well, if we were to analyze the function g of x and try to answer that question of in function notation, this is where function notation kind of fails us, because we were being asked to figure out essentially what is g of infinity, and that there's no finite answer there. I can't figure out the exact y value when x is infinity. But what's cool is limit notation calculus language does allow us to answer this question. So if I'm curious to know, okay, as x approaches infinity, which is saying as x gets bigger and bigger and bigger, and I can even zoom out just to make the point, you know, as x values get huge, on and on forever. The question is, like, what is the y value? Well, you might notice that it looks like if I'm on the function, if I follow it down, x is getting bigger. Look at the y value. I'll even start back here a little bit. So y is 1.9, 1.7. It's very quickly getting smaller, but not to 0. And I hope you're guessing in your head, if I were to keep going on forever, what's cool is if I go off to infinity, I can argue that, well, the y value would eventually be +1. And so we can say with limit language that the limit as x approaches infinity of g of x equals 1. And that's an example of where function notation just doesn't allow us that same analysis, but calculus language does. Limit notation allows us to kind of predict where functions will go, where objects will eventually get to, even if we're not going to figure out the exact value. So the last thing I'll do is a little more practice with just calculus language and how it looks. So quick multiple choice. So pause real quick. 3 of these are written incorrectly and 1 is written correctly. So your job is to figure out which of these A, B, C, or D matches this calculus language, the limit as x approaches 2 of the function f of x. All right, so A is really close, but A is incorrect because this says the limit as x approaches 2 and then of f of 2, which is just saying a y value. We want to analyze a function, that function as x gets closer to 2, so A is incorrect. B is saying the limit as 2 approaches x. We don't have a number approaching an x value because x values change, so I need to actually have an input value approaching a certain number, not the other way around. This is saying as x approaches f of x. Now, I don't think anywhere in calculus AB we deal with input approaching a function value. You could do it, but usually you'll see a limit value approaching a numerical value. So C is wrong. And then D is reading the limit as x approaches 2 of the function f of x, and that's the one we want. Okay, so that matches this language right here. So this leads us to the very last part where this is, again, great time to pause. I have 3 just written out in words, 3 limit language sentences. You should try to write what is the corresponding calculus language for these 3 sentences. Pause. All right, let's go. So this is saying the limits, let's start with LIM. You won't see the limit written out, it's just a shorthand for it. So the limit as x approaches, again, that arrow is saying gets closer to approaches, and the number is very clearly -3. And then of the function f of x just lets the reader know what function we're analyzing. Again, this is asking the same question. It's curious to know what is the y value. It wants to know the output on this function as we get closer and closer to -3, what is the y value? So limits are asking the same question as function notation with a slightly different form of analysis. Now the orange is saying the limit as x approaches -infinity. So it's a negative number, and in this case, it is negative sideways 8, which is -infinity, then of the function g of x. And the last one is the limit as x approaches 0 of the function q of x. So these would be the matching calculus notation languages for these math sentences. I'll stop sharing. Hey, you got a little introduction there. On the next video, we're going to actually be able to analyze that first limit we couldn't figure out. I'm going to show you because it's more fun than looking at me. Right here in the very first video, when I tried to figure out, hey, what is the limit as x approaches 2 on this function g of x, we had to really sadly say, oh, it doesn't exist, because as I get closer to here, it goes off to a super big positive number of positive infinity. As we get closer to here, it goes off to negative infinity. So we had to say, oh, this limit doesn't exist. In the next video, we're actually going to figure out how do we find a little bit more accurate description for those limits. So yeah, tune in for that. As always, ask questions. I'm here for you all.